everyone. Let's get our music going. Let's make that a reasonable. Okay, that sounds good to me. How does that sound to you all? Is that loud enough? Not too loud? It's hard to tell because all I have really with the stream is like the levels. Yes, the make it louder. You got it. Let's get in that holiday spirit. I know it's post Christmas for those of you who celebrated, but machine learning miss. So we do we want to keep our holiday cheer for just a little bit longer. Is that level better, Strawberry Jesus and Generic Crew? I'd rather I do have a trusty box of tissues just in case, as well as an even trustier COVID test. Mike gets cut out. There we go. All right. Just wiggled it a little bit. This is the most finicky mic when it comes to connections. This is even a new cable. And it's hopefully I just adjusted it, so hopefully now if I don't move it, if I don't touch anything, it won't cut out as much for you. So hopefully that works. Is it still cutting out a little bit? I hope I fixed it. Nevertheless, let's see here. Welcome, obviously, Strawberry Jesus, Loafbone, our trusty mod, Just As Good Joe, Hi, Generic Crew, a Hacker, Korova Milkman, Arrhythmia, NKLSPM, thank you for following, OKNE Blap, and V Galvez. So there is a non-zero chance, by the way, that my mom might show up to stream. So behave yourselves, by the way. I'm really hoping she does. I helped her set up her Twitch account. So I'm really hoping she shows up because that would be kind of awesome. Anyway, no, a hacker, sit down and behave. I'm watching you. Though my mom raised 2 sons, so she can also probably just handle it. Anyway, I hope that I hope that all of you have had a good holiday if your holiday season is over. Thank you all for your flexibility with rescheduling this stream because that was a bad cold. I had a miserable few days. But I'm better mostly. I have a glass of scotch here that'll get me through and my tissues. Thank you, Roger Gasmus, for following. So let's kind of recap a little bit here from before the break. We did linear regression, we did logistic regression, and we did some classification. And now you can see the updated, it's over here. It's over here on my monitor, but here for you. Our updated schedule. It's my mom! Hi, Mom. How are you? Yay, you stopped by. Yay! So today we're going to be doing ensembling. And because we did speed through at the end of the classification stream, it went a little long and we really sped through decision trees. So I want to do a bit of review of decision trees so that we're not all completely left behind. So let's see here. Alrighty, decision trees. And quick, make obscure Twitch references. Ooh, the extra trees. Okay, so we're not doing extra trees today, but we can. I think I mentioned them at some point. Okay, so let's get ourselves set up here. Thank you for following Digimon. So we are talking about decision trees to start out with. So we're going to do a little review. I know we talked about it at the end of last stream, like I said, but I really do feel like I sped through it. I skipped the math. You know, we don't skip math in this stream, so I'd like to do it some justice. Thank you for following Tsai Ming Lee. Welcome. Okay, so let's review decision trees, right? Let's give the example of if I'm going to take Hubble for a walk is a bad idea because I'll probably, like, he'll want to go for a walk no matter what. Let's say, am I going for a walk? All right. Am I going for a walk? Let's say we want to predict this. So in this case, what might affect this? Let's say maybe the weather is our real deciding factor here. So we might say, okay, is it sunny? Thank you for following Gamer85. So this is our prediction. This is what we want to predict. Doink. All right. And so let's start with, is it sunny? Will this work with trees in real life? No, sorry. And so let's say that this is yes, and this is no. Oopsies. No. Okay. So maybe our next layer of questions here is going to be, Sergio Maloney, thank you for following, is it above 80 degrees Fahrenheit? I'm a wimp when it comes to heat. All right, I'll just say it. Yes. No. So maybe this ends our... Where did red go? I have yellow here. Who's been messing with my pen colors? All right. So let's say... No, I'm not going for a walk that's over 80. So that if it's not over 80 and it is sunny, we go for a walk. No walk. Okay, and if it's not sunny, so it's cloudy, so maybe we ask, is it raining? And this is just an example, so don't get caught up too much. I'd last in Michigan. I'm good with the cold. That's the strange thing. I just don't like when it gets very hot. Is it raining? So we've got yes and no. And so here we'll say again, no walk, walk. Okay. So any of those flow charts that you've seen kind of on Twitter or wherever, Reddit or something, that's like a flow chart of like, should I do this, right? And a lot of times they're used kind of sassily where like everything leads to the same outcome. Those are decision trees. So now we're just going to look at it in terms of math. And we need some terminology first before we get started. And let's see. Happy holidays, Ian Alex Hart. I can talk. I got to get back used to this. All right. So let's learn some terms here. So this right here is what we would call our root node. All right. It's the first question we ask. It's the first thing that we split on, okay? And then after that, what color did I use for these? I used light blue. We have decision nodes. These come after our root. Our root, right, is the start. These are kind of our later branches, right? And then down here, we have, these are what we call our terminal nodes. I see it more commonly referred to as a leaf. Okay, so if I'm talking about leaves, terminal nodes, same thing. So the biggest thing, right? Decision trees work from the top down largely. Okay, so we start at the root and we work our way up, or I guess in this down, up in terms of width, down from the top. It's all relative, right? And there's a rule at each split, right? So here it's easy. We have the rules laid out for us. Is it sunny? Is it above 80 degrees Fahrenheit? Is it raining? That's really, really easy. But one of the things that we're really going to focus on for our decision trees is how do we make these splits, right? So if actually, and here's what spoiler, by the way, I'm going to try to not clear the Blackboard so I can save it as an image and put it on the GitHub. Okay, so I'm going to try to actually make my notes a little bit better than usual. And so this is an example. Because I have been clearing them and I apologize for that. Welcome, Vintage Primer. Thank you for following. And Simon Lee, you say, are the nodes and leaves in decision trees programmed the same way as trees in regular non-AI ML programming? So, no. Because I think what you're thinking of probably are things like binary trees, right? And so that's primarily used for searching and sorting. So in this case, one of the similarities is that we are, in a sense, sorting our data, kind of. But instead of sorting it for looking for a specific value, we're trying to group our data based on rules. And so it's going to be a little bit different because we won't know. Like, this is a really prescriptive example because we already know the questions. Like, I made the questions up, right? But if I have the data set that we used last time, which was our iris data set, right? So it was a data set of 3 different species of iris flowers with measurements of their sepals and their petals. If we have that data set, I mean, I'm not a botanist. I'm not going to sit there and know immediately, oh yeah, we need, sepal width above 1/2 inch or something, and that's how we're going to start. We don't know the rules. So one of the tricks or one of the challenges is how do we mathematically come up with these rules? And so that's where we're going to start. And there's a couple of different ways. And I guess maybe for people who are watching this, I should have like an arrow so they know where to go. I don't know. I've never done this before. Okay. We'll see if I run out of room. Thank you for following 25 Wolf. All right. And hi, Ronskian. Welcome. Okay. So our question now is, how do we figure out the splits? How do we split our data, right? Because the goal is to split our large data set into subsets of the data. And that those subsets are determined based on a rule. Well, what rule, right? That's kind of the intuitive first question. And so the first rule we're going to talk about is something called information gain. Okay? And to understand what information gain is, we need to start out with figuring out what entropy is. And kind of your if you're from physics, if you've learned about entropy in computer science, all of those intuitions are going to serve you well here. Entropy is simply a measurement. It's the measure of randomness in our data set, in this case. All right, good, you can see that. And so what does that mean for predictions? What does that mean for machine learning? Thank you for following Tree Fury. You have the perfect name for this stream. Sorry. All right, a little bit of scotch. This is literally to keep my voice here all day. Okay. There we go. Ooh, RKYRK. I'm not even going to try to say that. Welcome. Thank you for following. All right. So what does a measure of randomness in data even mean for predictions? Okay. In this case, what it means is that higher entropy, okay, this is our little example here. High entropy means it's going to be difficult to make predictions from the data, all right? So difficult to make predictions. So let's bring our minds back for a second to linear regression, because I find that especially when folks are learning and they're just figuring out what all this stuff means, the linear regression example is the most intuitive, right? Like most of you, unless we have some extremely underage viewers, have learned like what a line looks like on a graph. So if we have, that'll do. All right. So this is kind of the example that we learned in linear regression, right? Linear. Ooh, I can make my handwriting tiny. Okay, hopefully you can see that. So if we have a high entropy example, right? Our data set, well, real randomness is impossible, but I will do my best to approximate that. Okay, so this is high entropy. It's hard to make predictions. The data looks random, right? low entropy, very low entropy, right? Might be, can I make a straight line? Oh no, people are watching. I could do it, yes. Exactly, a scatter plot, precisely. And that is a high entropy. Oh my lord, I can't even draw a straight line, okay. No, I could do this, hold on. Okay, this thing is tilted a little bit. I swear, all right, hold on. I did it, all right. This is low entropy. Okay, so my head's a little bit in the way, but hopefully you see that. Real randomness is possible. Have you met your 8-year-old? Well, they say that the only way, right, that you can find true randomness in his observations of physical phenomenon. So maybe your 8-year-old is 8-year-old behavior is enough of a physical phenomenon that you measure it and it's truly random. Root Knox, welcome. And you say ensemble models, you come from a French background. I do not actually. I speak French terribly. But no, so ensemble in this case is actually the technical term for what we're going to get at. So I'm doing a little bit of background here on decision trees first, but as a slight spoiler, ensemble models are a little bit of a misnomer because it's not a single model necessarily, but it's where we pull together a bunch of different a bunch of separate machine learning models, and we have them act together in some way. And so in this case, we're going to be talking about random forests, which, if you can make the language connection, a random forest is just a bunch of decision trees. Write me Cass. Welcome, and thank you for following. Okay, so a keyboard combo with mouse. Well, I got a little thing. So I'm very basic here. I think if I were to try to learn, there's even buttons on here and I have no idea what they do. So go easy on me. All right. So if we were to talk about how our data is distributed, which is what this is, right? So we have like a really nice linear distribution here. We have kind of a random scatter plot. And here's kind of more of an like nice, not quite perfect, but maybe low medium entropy. So if we are going to, oh yes, no, wait, what? Oh God, no, please stay. I'm so bad at this. All right. So if we're to talk about the relationship of entropy to the probability of a particular prediction. So let's now go and think about the case of a bag. Let's say we have a bag, right, with a bunch of marbles in it. This is that classic elementary school probability example, all right? So let's say we got a bag of marbles. Okay, and so if we have, let's say we got two colors, we're gonna have green marbles, and red marbles. Because the holidays, gotta have our like happy little, and it's gonna be a bucket because I can't draw a bag. Ah yeah, art. Okay. So if we have, we've got six marbles. My mom's like, no. She's an elementary school math teacher, so she's probably like, no, please. I don't want to look at it. Bear with me, Mom. All right, so let's say we have 6 red marbles. All right, 6 red marbles. What is the probability, P, of pulling a red marble? This is really easy, right? It's 100% or 1.0, right? 100%. Because all we have are the red marbles. So how easy, exactly, just as good, Joe. So how easy would it be to predict? Right? So hold on one second. So when P is 1, okay, so when P is 1, entropy is very, very low. It's super, super, super easy to predict, right? And thank you for following iMagic007 and GVSTU. Welcome. Okay. So what about the example where we have I'm so glad I didn't pursue a career in art. All right. And let's talk again. What's our probability of getting a red marble in this case? Scotch break while you all figure it out. Zero, exactly, right? Of course. Zero. We got no chance. No chance. Well, how easy, again, is it to predict? That is absolute. It's all or nothing. Our entropy is really, really low. Well, what about... Shoot. Can you see that? Yeah, okay. Tiny little bucket. I don't know why I keep drawing them with really fat bases, but they're wide bottomed. All right. What is the probability here of getting a red marble? And Tislav, thank you for following. You got this, chat. Bringing you back. Exactly just as good, Joe. 0.5. Right? 50%. Or 50%. And so what that means is suddenly it's really hard for us to make a prediction about whether or not we're going to get a red or green marble. We have literally a 50-50 chance. That's a guess. That is a flip of a coin. And so our entropy is going to be highest. Oh gosh, can I do this? Can I draw? Oh yeah. Kind of like an upside down quadratic kind of relationship here. So our entropy is going to be maximized when our probability, when our data is evenly split, right? And so one of the ways that you can make decisions in a decision tree, you can find out those splits that you need to make, is based on minimizing entropy. So if we ask a question of our data and we split our data, just like in the decision tree back here. Oh, this is nice though, because now I can go back here. Just like here, am I going for a walk? If we ask, what color am I wearing today? Our data might be completely random. That might not minimize our entropy. But if we're able to, or if our goal is figuring out no walk, and asking a question lowers the entropy, it starts to group our data, it starts to pull those two classes aside, then we're able to continue making this decision tree. Thank you, Cookie Rains and Motown Andy, for following. Okay, so what does the math of entropy then look like? Yes, Simon it's a great way to make actually, so I ended up not using that, if I remember right. Hold on, I will link you with what I used to do subtitles. So I believe I tried that. I had mixed results. I had a much better, I can't remember if this is actually the same thing. This is what I use now. Okay, so let's talk about the math of entropy then. What does this look like in math? We have this graph, but what's really going on? And let's start with the simpler example right now, which is entropy for a single feature. All right? And that's probably, let me just put a space there. And so for those of you who are coming more from a math background, can just drop it over the donation and not block the screen. Oh, yeah. Okay. So for those of you coming from math or physics and not from machine learning, features are our X values here. Okay, so we're talking classification still, we're aiming to predict a label, a Y. So when we're talking about like linear regression over here, drawing a line, our goal is to say, given some X, can I predict what the Y is? Right? And so our x's here, given x, predict y. Oh, that's a j, that's not a y. All right, the difficulty, right, is that x often, that's messy, there we go, is a bunch of different things. And this is what we call our feature vector, okay? So in this case, it might be like for our Titanic data set, right? We worked with a data set for a little bit that was all of the people who died and survived on the Titanic. So if we're trying to predict Y, did they survive, yes or no? Our X might be their age, the class of their cabin, their gender, how much their ticket cost, how many siblings, I think was one of the data points. So we're able to, instead of just having like in your standard algebra linear regression, your y equals mx plus b, right? Where we have just one x. Here, really what we're talking about is a lot of different features. So when I'm talking about features over here, just think about your x's. Oh no. Stay. Okay. So entropy for a single feature. This is your y equals mx plus b scenario. And let's see. How do you minimize through some optimization function? Hold tight, just as good, Joe. We're getting there, I promise. David Ames. No thinking about those kinds of x's. This is your independent variables. They're way more fun than x's. All right. So let me think. Ideally, our goal, right? Our goal is to get entropy as 0, right? So our leaf node, our goal, like the perfect tree would be where entropy is 0. League of Evil X's. No, none of that. Okay, so let's start with a really simple kind of example, which is, will it rain tomorrow? And let's say that there is a 75% chance yes, 25% chance no. All right. So get ready for some math. Stay with me though. I'm going to write it out first, then we'll go through it. So do not panic. Okay. All right. So our entropy of a given state, and all that means is our state here is it's raining. Okay. Is going to be, don't panic. It's just a sum. Okay. Okay. I mean, sniffing glue, you can't do. Thank you for following Radulo Cut, Comboard, and Japstock. I'm sorry I missed you. I was focused on the math. All right. So P here is just our probability. All right. So it's the probability of that particular feature or that particular state, right? And we're going to sum that up for both of our options here. Okay. So really, if we expand this, right, the entropy of like rain is going to be negative probability of rain. How did I do this? No, probability of, let's do not rain first. Doesn't matter, but I'm just trying to stay consistent with my notes. Negative probability of it not raining times the log base 2 of the probability. Oh my God, why am I writing out probability? It's the cold meds. Don't judge me. Of not rain. Minus probability of it raining, log base 2, probability of it raining. Okay. So what does this look like? Let's fill in. We've got our probabilities here already. So our entropy of rain is negative 0.25 times log base 2 of 0.25 minus 0.75 times log base 2 of 0.75. All right, and thanks to magical, I did the math before stream, this comes out to about 0.81. That's a fair amount of entropy, right? We've got not the most entropy ever, but it's pretty high because it's not perfect. It's not 0 and 100%, but thankfully it's not 50-50 either. So fill that in for completion, right? Okay, so this is what it looks like for a single feature. But most of the time when we're employing machine learning, right? Oh, this just keeps going. This is awesome. We're gonna have entropy for multiple features. Or of, I guess. Not for. This is not like a service. Entropy of multiple features. All right. And I'm not going to work an example for this one. It's very, very similar in form, but I will give you the equation so that you have it for the sake of being, you know, thorough. Thank you, Captain Obvious, for following. Okay, so in this case, we're going to have a state S, and we're going to have our feature vector X. Okay, so we have X is our feature vector, and we're going to have our state. Okay? So now we're going to have the entropy of our state and of our feature vector. All right? And what this is going to be is this going to be another sum. I swear I can write sigmas normally on my own paper. Whatever. Where C here is going to be, it's going to be one of our features. The probability of C times the entropy of C. So it's a little bit recursive, but not fully recursive. But all right. And this is how we determine the entropy of having multiple features. Is we're going to take the probability of that particular feature happening times the entropy, like the single entropy of that feature. Playcraft 2, you say start over, I just got here. That is what the VOD is for, my friend. All right. So information gain, right? So if we, oh no. If we go back here, right? All the way back here. Information gain. Have I said that word again? No, you're probably, what the hell? Like you just talked for 10 minutes about entropy. All right. Information gain. Information gain is one of the ways that those splits are made. So typically, I guess you could, I think there are some trees that split solely based on entropy, but typically information gain is used instead. Thank you, Metzger9, for following. Okay, so, for example, information gain, let's actually just define it first, measures how well a particular rule, what am I doing here? Nope. A particular rule separates the data. So what that might look like is, you know, maybe we have, I'm going to draw kind of like a conceptual decision tree here, so bear with me. Let's say that this is our data. And it's all mixed up, right? Oh no. We're in a high entropy situation here. And let's say that we try. Let's you know, okay, let's try a split. And after splitting based on a rule, this is kind of what our data looks like. So not super great. But clearly it's trying to split. We have more red data. Let's put even more red data, make it a little more obvious. Red data here. We have more green data here. So is that the best option? I don't know. If we instead try, Let's see, am I below? I'm going to run into my own head, aren't I? All right, so hold on. Instead, if we try a split, let's make our holiday themed data here. I'm going to milk this for as long as I can. I love this time of the year. Thanksgiving is actually my favorite holiday, but this is just such a wonderful time of year. All right. Nobody go through and count all the dots and yell at me for them not being equally distributed, please. Okay. If instead perhaps we make a smarter decision, okay, and we pick a better rule to split our data. So instead of asking about what color I'm wearing for our am I going for a walk, we ask about, you know, the weather. Maybe we actually get a situation that's more like this. This is a much better split, right? This is a great split because it's not perfect, but still we have started to sort that data more effectively. So in each of these cases, can I fit them both on screen? I can. All right. So in this case, we have higher entropy after the split, and we have lower information gain. Here, we have lower entropy. Thank you for following Code Brewery. And higher information gain. Okay, so there kind of is like an inverse relationship between the two. And thank you, Playcraft, too, for following as well. All right, so what does the math look like? And let's see, David Ames, you say, can you recommend a programming language to learn first and an online course that's fun and easy to follow? I always recommend Python. I really do. If you haven't done a programming language before, the syntax is intuitive, it's readable, it's easy to get started. There's 1.5 million different, Python classes out there. I like recommending to people who don't have a computer science background or haven't done a lot of coding. I like to recommend MIT's Intro to Computer Science class that's on YouTube. They teach Python, and they're also teaching the fundamentals of computer science as well. And so you kind of are getting 2 for 1. I will just caution that the way that the professors, at least the one that I ended up watching, were teaching, the great professors, but they write their Python code like it was Lisp or C. And so like the formatting isn't kind of what you would see with Python standards, but whatever. Like, yeah, I think it's CS50, maybe. I don't know. I thought it was like, I'll look it up for you. All right. I'll look it up. Let me actually see if I can find the link. Hold on. Just for you, friend. YouTube. Computer science, MIT. No voice. Stay with me. It's 6.0 technically, which, here you go. That's the one that I liked, but in any case, so let's go back to information gain, right? Like I said, there's kind of this inverse relationship between entropy and information gain. So when we're using information gain, we're looking to maximize it. We want to make splits in our decision tree that maximize our information gain. So what even is, like, what's the math here? Okay. And the information gain here, I'm going to call it IG for simplicity, right? And we're going to have the same thing. A state S, feature vector X, is simply the entropy of that state minus the entropy of that state and that feature. And so what you could think about, like, what this really is saying, if I were to translate this into English, it's saying that information gain is equal to the entropy before we split minus entropy after we split. Okay? And so think about it for a second. Entropy before split, this is probably going to be very high, right? Especially if we're talking about our root node. Entropy after the split, this is what we want to be very, very low. We want to be lowering our entropy. We want the change in entropy. The change in entropy. We want that to be very, very high. We want the entropy to be going down. And so that is what information gain is summarizing for us. Now that I've just spent all this time telling you all about it, I have to break some hard news to you, which is that we're not using information gain in our decision trees. I know, I'm sorry. Nevertheless, lots of really prominent decision tree models do use information gain, so I wanted to kind of walk you through it so that you understood how we get from entropy to information gain. The other way is something that we also talked about last time. I kind of moved fast, so it's called the Gini index or Gini impurity. Okay, and so this is getting back to a question. I'm so sorry. Someone did ask, and I forget who asked it. Was asking like, well, do you have like a function that you're trying to optimize here? This will feel a little bit more intuitive then, because you can think of Gini index or Gini impurity as the cost function. So if you remember from before Christmas, right? For those of you that celebrated, I scrambled my brain a little bit. I relaxed very nicely. The Gini index. What was I saying? Hold on. From before Christmas. Right. Cost functions. When our models get very complicated, it gets harder and harder to define what we're trying to minimize, right? So if you remember back to linear regression, when we had, actually, since I drew all those wonderful plots right up here, we talked about how one of the ways that we could talk about what we wanted out of linear regression. It's easy to say, I want the line to fit the data. What does that mean in terms of math, right? We're trying to minimize the average distance of each of these points from the line, right? And that's how we got our, square root of x squared plus y squared, simply our Pythagorean theorem, right? That's what we used to tell our distance from each of these points to the line. And then we said, that's our cost function, essentially. Scotch nog? I'm not drinking any eggnog. My scotch is straight right now. My scotch is neat. It is the very last bit of Talisker. Rest in peace. I finished the bottle tonight. Alas, I'm fully out of Talisker now. Never thought I'd see the day. Thank you for following. Tima Fane, Mifraz, and Leova. Sorry if I missed any of those follows. I tend to get in the math zone and I don't hear anything else. Right. And so in that case, our cost function, our measurement of error that we were trying to minimize came from that Pythagorean theorem. It came from the distance of each of these points to the line, right? So this is going to be kind of like our cost function for a decision tree. And so you get it by subtracting the sum of the squared probabilities of each class from 1. What? Let me write it out and then we'll talk about it. Gini index. You subtract from 1 the sum of the squared probabilities of each class. Do I stream only on Sunday? Well, my friend, I have good news for you. I have a schedule command that you can use in chat to see the schedule. This is the current schedule for the 12 days of Machine Learning Mist. After that, we'll be returning to our normal stream schedule, which is Science Sundays, Math Mondays, Viewer's Choice, that means all of you get to pick for Tuesday, and then I learn game development on Thursdays. Sometimes there are some excess streams in there, but I'm trying to have a life a little bit, have those days where I just binge my video games, so I need some of those too. Thank you, You Ain't Dank and Sasink Thapa for following. Okay, so one of the little caveats that I should put here, right, is that this only works with, it's going to predict, or it's how to put this, it's going to work with categorical variables. So this is kind of, it's used kind of in a pass-fail situation. Okay. Captive, thank you for following. All right. And so the way that you can think about this is that we're summing up the probabilities of getting each of the classes, right? And subtracting that from 1. So let's think about that. What would our ideal case be? Well, our ideal case would be the probability of one of the classes is 1, and all the rest of the classes is 0. So if we square that and we subtract it from 1, then the Gini impurity is 0. So this is something we're looking to minimize, right? And if it wasn't already clear from cost function. So kind of think through whenever you see math like this that you don't understand, that you're like, oh dear God, there's like some, Greek letters and there's a lot of stuff going on. The way that I like to do it is I first like to break it down. And so I translate it as best I can. I'm like, hey, G is Gini index. This is a sum of probabilities. What does this even mean? And in this case, we know what we want. We know the ideal, that extreme scenario where we've split perfectly and we have a probability of 1 for one of our classes, probability of 0 for all the rest. So then just plug it in and be like, okay, well then what value do we get here in our ideal situation? Probability is 1. The rest of the probabilities are 0. 1 minus 1 is 0. So this is something that ideally, in the ideal case, the Gini index is 0. 1 minus 1. What video games do I play? Everything that's not a racing game or a sports game. Unless you combine racing and sports games, and then I like Rocket League. But other than that, I pretty much play everything. Baby, how you say it? I had to pick up a little linear regression at work to make a sales report. I was trying to place what this reminded me of. Yes. So we did a video on linear regression. That was day 1. The VOD should still be up on Twitch. I am downloading them and putting them on YouTube. So if you missed that, don't worry about it. They will be up on YouTube. The square magnitude of a probability vector. Well, you came right in time. And CFig, I do not know the Racket programming language. Okay. There are a lot of other ways. It was sneezing. This cold. I'm doing better, I swear, but it just creeps up on me. There are other ways of splitting. There's things like the gain ratio. There's a chi-squared approach to splitting. We're not going to go into them because otherwise we'd be here all night and we wouldn't get to any programming. We wouldn't get to any fun. And why did you all even show up? You came here for random forests, right? So let's see. Oh, okay. So we explained those. So decision trees. I guess now we can move down here to is that kind of, should have paid attention to what the zoom was when I was writing previously. All right. Here's why you were here. Random forests. Woohoo! All right. So this is the first ensemble model that we're going to learn about. And like I mentioned earlier, I gave a little bit of it away, but an ensemble model is just a bunch of machine learning models working together, okay? So in this case, we are going to make a forest of decision trees. And you might ask why. We have decision trees. They're great. They work so great. They're beautiful. They're perfect, right? No. Does anyone remember from last stream? And I know it's been a couple days. I know Strawberry Jesus, now they are. So I don't have the whiteboard files for streams days 1 through 3, but somebody asked me in the last day if I would save these instead of just clearing the Blackboard each time. So that is why, as you can see, I'm attempting to keep all of my notes on the same thing, and I'm going to save them and I'll put them on the GitHub. Okay, so can you remember from before break last stream, or if you're familiar with random forests and decision trees, what is the main downside? What is the Achilles heel of a decision tree? What's the big problem that we talked about last time with decision trees? because they're great. They're explainable. They're simple. They're straightforward. They're intuitive. Like, we've all seen those flow charts. Oh shoot, I'm sorry, Strawberry Jesus. Yes, that day 3 and day 4 will be up after this stream. Last stream I really started to not feel well at the end. I literally like stopped streaming, whatever, got in my PJs and slept and didn't leave bed for the next probably like 36 hours. So thank you for your patience. I will put normally I upload the code after the stream. And yes, Mediocre Gamer, Psychic, exactly, Strawberry Jesus, you both are perfectly answering here. The main problem is overfitting. And so we've talked about this before in some of our other models. Overfitting, V. Galvez, hydrate. Cheers, friend. It's my last bit of Talisker. Okay. Froid.dev. I don't even know if, like, seriously, I'm sorry. Freud.dev. You gotta tell me how to say your name, so I stopped Frenchifying it. Thank you for hosting. Thank you so much. And thank you, KHM3R, for following. And Julian, I'm sorry, Huian. I think I might have missed you as well. All right, so the problem is overfitting. And if you remember what overfitting is, but let's go through it. And don't worry, KHM, you say, what is random forest? You're in the right place. We just started talking about it. Overfitting is the problem where our model complexity gets very high, right? Maybe we have a lot of features, a lot of parameters, right? And our model fits perfectly to our data, but isn't able to predict well on new data. Right? And so we've talked about this before, how we might take our data, happy little data block here, right? And we split it into our train data and our test data, right? So this is what we fit the model to, right? We fit the model to this, but we test the model on this. Now, we haven't really talked about this, but usually what you do is you actually have a third one. And this is called a whole bunch of, I think somebody called this like the development set. There's a bunch of different names for this. But essentially what you want is like, we'll call this our real test. And I just goofed it already. This is... A lot of times you'll actually take an entirely different data set, because even when you train, test, split, you still run the risk of overfitting because the data is still coming from the same data set. So if you think about like a computer vision model, right? The example that I gave of this before is the model, I love telling this story, but this was a model that they trained it to recognize the difference between dogs and wolves. What they didn't realize is in their data set, it was performing amazing. Like it just, this model could predict wolves. And then they started, testing it actually on other data and it was doing really poorly. It was like, what, why is it predicting wolves where there is no wolves? Why is it failing to recognize these wolves? Well, what it had actually done is it had overfit to the data that they were training on. And it actually was predicting whether or not there was snow in the image, because the data set that they used had a bias. It had, what we were talking about in linear regression, had a multi-collinearity between the label, wolf, not wolf, and one of the features, which was, is there snow in the image? And obviously that's not how computer vision works. It doesn't necessarily work like feature-based like that, but you can kind of think of it conceptually in that way. But this model failed to actually find the difference between wolves and dogs because there was a bias in the data set. And so that is a good example of overfitting, where your model's performing amazing on the data that you've trained, split on, train, test, split. But it performs really poorly when you actually test it on new data. And we got some new follows here, so thank you. Whale Bites, Chili Paste, Bright Horizon, Gams TV, and Kieran SCO for following. Okay, so Why are we talking about overfitting? Well, because the holy grail of machine learning is a model that can generalize, right? So we want our model to actually learn. We don't want it to predict whether or not there's snow in the image. We want our model to actually learn the difference between a wolf and a dog. We want it to be able to take those general rules and apply them to data it's never seen before. The problem is, as Strawberry Jesus, Arrhythmia, and Mediocre Gamer very accurately pointed out, decision trees have a fatal flaw, which is that when you allow them to grow too deep, so when you allow a lot of splits and they get very, very big, they tend to overfit a lot. And there are two things that you can do to solve that. You can prune them. That's literally what it's called, pruning your trees, which means you limit the number of decision nodes. You limit the number of splits that can happen, the depth of the tree, or you do a random forest. The idea behind a random forest is that if we take a bunch of decision trees, and maybe this one overfits for snow in the image, but maybe this one overfits to the color of the wolf or something. Well, if they're all overfitting in different ways, we can average that out by having a lot of different decision trees. Okay? And so as I mentioned though, actually I should probably make this a little bit of an aside here. So we want a whole bunch of trees. Why am I drawing this? Because it's fun. We want lots of different trees, hoping that the flaws of each individual tree will average out. Okay? If we are doing classification, then we are going to use the mode, so popularity vote, if you will, of the outcomes of all these trees. So if all these different trees say, 3 of them say we're taking a walk, one of them says we're not taking a walk, well then we're going with we're taking a walk. If it's regression, we're going to predict the mean or the median of the predicted value. Okay, so how do we build them? How do we build decision trees? Well, how do we build random forests? There's 2 ways to go about it. There's doing it manually, and then there's getting a model to do it for you, okay? And one of the common ways to get a model to do it for you is something that we call bagging, which is kind of an amalgamation of Bootstrap Aggregation. And thank you for following Jacino33 and Uppermost. And you ask, is ML the same as AI? And thank you for following Theo, the other drummer. ML and AI are different. And so the way that I like to explain it, and I'll do this really quick because we talked about this in the first video, is that if this is AI, this is ML, right? So maybe we've got our unsupervised learning, supervised learning, RL, right? AI, what's here? This is what we often call rules-based AI. And so this is where you have an AI that is essentially just reading a giant book of if-then statements. So if this and this and this and this and this, do this other thing. But if this and this and this and this, do this other thing. You could theoretically approximate, artificial intelligence with just a very exhaustive, set of conditionals. The limitation there, of course, is that when presented with new situations, that kind of artificial intelligence will fail. So machine learning is where we're actually aiming. This is where we're aiming to generalize, right? We want to create a model that will learn something, will come up with the general principles that it can carry forward and apply to new and unknown situations. So I'm going to erase this real quick, though, because we did talk about this in video number 1, I believe. So you can check out that VOD if you want more details. My cough. Do I keep VODs for past episodes? I do. They're gonna be on YouTube. So I gotta get my butt together here and put them on YouTube. So those will be, I'm in the process of downloading them. This is all the scotch I have left though. I'm trying to like ration it. Okay. All right. Drink more scotch to help my cough. Oh, yeah. Okay. So what is Bootstrap Aggregation other than something that sounds really, really cool? All right. This comes from something called Bootstrap Sampling. What is a Bootstrap sample? Well, Bootstrap sample is a random sample of our data. You might be like, wait, we've done this when we shuffle, test train split. Well, the difference here is that we have replacement. What does that mean? That means that a random number of our sample data, right, will be replaced with like duplicates of the other ones. So instead of like, and we're gonna do this, I'll show you an example in a second. It'll be the same size as the original sample, but it will have some things replaced. And actually, this is a good point. Let's do the code so you can see day 4. Let's do the code so that you can see kind of what I'm talking about, and you're not like just listening to me ramble at a blackboard. Oh no, where did stream go? There's stream. All right. And FX Streamer, we will be doing neural nets. You can check out the schedule. That is going to be, looks like we're going to be doing Neural Nets 101 on the 2nd of January. So stay tuned, my friend. We have to, the 12 days of machine learning, we gotta start with the other kinds of models so that by the time we get to neural nets, you actually understand a lot of no today now. Nope, ain't gonna do it, friend. You gotta stay tuned. Fun things happening later. All right, so Bootstrap sampling. What does it look like? So, did Sinterklaas bring you anything nice? Well, the green screen. I also, let's see. Bueller, brain. I got some nice clothes from my mom and some earrings. I'm wearing the earrings that she got me. She was in stream. I actually don't know. I think she goes to bed a little bit early, so let me actually see if she's still here. Nope, she went to bed. Oh, well. It was very sweet of her to stop by. Nevertheless, let's see, what else did I get? I got a bunch of books I've been really wanting to read. I got a bunch of stuff for the kitchen, which I know that sounds really silly, but like I love cooking and I've really gotten into drying and preserving things from my garden. So I got a lot of stuff for that, which was really, really awesome. I'm really congested and I can't think of even the process of opening gifts right now, let alone what I got. I remember getting a lot of things and I was really excited and I loved all of them. My brain right now, unfortunately, is in machine learning mode, so I'm sorry. I can't remember all the things that I got, which is terrible, I know. Okay, so if we were to create, let's create a fake sample. All right, so this is the sample that we're going to be working with. All right, so this is what it looks like, right? The numbers 1 through 20. So I have not seen that book, The Alchemist. I learned from a combination. I do like books, and I have a couple of really good textbooks, but mostly I learn through building things myself, largely. But I have a pretty rich math background. So, yes, zooming in on the code, thank you. I usually get this. 150 seems to be the percentage you all like. So let me know if this is still too small. And I have both Prime and Netflix, actually. All right, so we're going to be using NumPy's random choice method here. so this is what Bootstrap sampling looks like, all right? This is our data, right? We're going to pretend this is our data, that is just the numbers 1 through 20. And we've now picked 1 through 20 randomly, but we've repeated some. We've cut out some of them and randomly doubled others. So it's kind of like you're dropping some of the data and you're doubling some of the other data. And the goal here is that if we have a random forest, and instead of just training all of these trees on the same data, which wouldn't really do very much, we can instead train on Bootstrap samples. And then what we're hoping to do is kind of average out some of those errors and some of that overfitting. Thank you so much for following. Coyote Barracuda, I think I missed you. Thank you for following. Stern Finger and FX Streamer, thank you so much for following. And Illicit Gamer, thank you. Okay, so let's import the basics real quick. So I'm just gonna copy this because I'm tired of typing it out for every stream. All right, and let's get our data. We're gonna use the same data that we did last time because the goal of an ensemble model is that it has to outperform the models on their own. And so I want to say yesterday, day 3, we got about an average, I want to say, of like 76%, if I'm remembering correctly. And you can control the number of replacements, or you can leave that random, Strawberry Jesus. Might have to make tea. Let me see. Actually, hold on. All right, give me 1 second here. Oh no, we lost our music. I was wondering, it sounded very quiet. Hold, please. There we go. Hydrate. I don't have much hydration left. Okay. You say you like Numpy and Skippy for... I like Skippy for sci-fi. That's cool. NumPy, SciPy. I don't know. I've heard it so many times that it kind of is just ingrained in my brain a little bit now. Okay. So let's get our data. And like I said, we're going to use the Iris dataset again. This is one of those classic datasets for machine learning, because those of you who are interested maybe in someday pursuing a career in machine learning engineering or in data science, there are the hallmark datasets. So I want you to be familiar with them because 1, you might see them in interviews, and 2, people might ask you questions about them. So now you've been familiar. We've gone through the Titanic dataset. We've built models based on it. We've gone through the Boston housing dataset. We built models based on that. And we've gone through the Iris dataset and built models based on that. Bye, Third Tier Gaming, and may the fan bless you with clear nostrils. Thank you. I'm going to get there someday. I feel better. I really do. It's just like, ugh. Okay. I just want to clear my throat all the time, which is really annoying. Okay. So let's get our data. Does it load? No, it's load. Oh my god. Okay. Data sets. It's Iris. Oh my god. Load Iris. Whew. Alrighty. One of my teachers said it's good to use a data set you know really well when learning to Tenn. Exactly. Arrhythmia, that's another great point. Kaggle has some great ones, but whenever I'm trying to learn a new type of model, a lot of times I'll go back to a data set that, 1, I know. The other perk of these, right, that we talked about last time is a lot of times they have the data set's already cleaned and they're already balanced and they're designed to be used for machine learning. So it's really, really nice because instead of learning, say, linear regression, and you use a real data set and you're like, wow, this model is performing like crap. It must be a bad model. It's probably data problems. By using good data to start out with, you can at least see how the models work and what you should expect. Thank you, Litho90 and Edgebird for following. I will say, we're gonna soapbox briefly. Sorry, friends. Soapbox. Because this is one of my pet peeves with boot camps, is that they only show you the clean data And I really feel like a lot of times, and you Google, if you were to Google linear regression tutorial Python, you would see pretty much only, at least the top 50 results would be using your Boston housing data set, your Titanic data set, which is what we used here. But we've used it here because I have streamed now ad nauseum on the process of exploratory data analysis and how you clean your data, how you prep your data to get ready for machine learning. And one of the things that really bothers me is that I haven't seen that in boot camps, really. I haven't seen that in tutorials. Largely, it's just use this nice, clean data set that's going to give you great results. No one teaches you how to take, the world's crappiest, sloppiest, messiest data set and work with that. Because that's what the job is like. That's what it really is like, is taking data that is full of, null values, horribly imbalanced, missing data, all kinds of problems, and building something using that. So keep that in mind, that all the data that we're going to be using for the 12 days of machine learning miss is cleaned and wonderful and nice, but that's literally because we have done so many streams at this point on exploratory data analysis. So you all should know better now. Thank you, Flamed Eye and Charge in Love. Is it weird? I kind of like cleaning data. I feel like it's kind of like a masochism that just grows on you. You start out hating it, and then you realize that that's what will make or break the success of a machine learning model. Literally can't tell the difference because I'm stuffed up. Sorry. Thank you for following, Jesse Skinner. That is the most powerful step. I honestly, it's more important than feature selection. It's more important than hyperparameter tuning. That's the fun stuff. Don't get me wrong. That's what makes you feel cool. But what makes or breaks a machine learning model, it's the crap in, crap out, right? Clean your data, normalize it, figure it out, feature select. Those are going to be the things that take forever and also are the most important. Quixotic Robot, thank you for following. Well, Arrhythmia, I think they're trying to get, most boot camps, at least that I've seen, are about padding your resume. They're designed so that you can come out of a 12-week course and pretend that somehow in 12 weeks you've gone from knowing nothing to being ready to get a job, which I think it's given you a solid foundation, but you learn the most by doing. So, in any case, I could rant on and on and on about boot camps, but Sinocron, this is a Jupyter notebook. So we're going to be using it for the smaller models because it's snappier. You get immediate feedback. I can show you line by line what the code's doing. For some of our bigger models, we probably will just go to a normal IDE. But for the smaller ones that run faster, I like being able to show you stuff line by line. So, yes, so today we're doing random forest models, but we'll be doing some more complicated computer vision and natural language processing models in the future, and those probably, they might break a Jupyter notebook, so we'll see. Yes, Jupyter notebook, there's customization options just as good, Joe. It saves you, trust me. All right, so let's speaking of pandas, speaking of how much we love pandas. How did I set this up? There we go. Feature names, yeah. This is code I'm copying from the yesterday, day 3. So if you see me just kind of reading my code, that's because I don't really want to do it all over again. So, all right. Thank you, Carl Mint, for following. You say, baby, how you say, makes me want to go back and check on my boot camp classmates. Yeah, I kind of wonder. I took one to have it on my resume because I was self-taught, and so I was like, I have to have some kind of rubber stamp on my resume. So I took one. Then I looked at the professor, who was awesome. The teacher was wonderful. She was great. But we were at the same place in our career. So I was kind of like, I didn't get as much out of it that maybe somebody who hadn't done machine learning or data science would have gotten out of it, just because like I had been doing data science for several years at that point. But I needed the like, you know, line on my resume, because my graduate education is in astrophysics and my undergraduate education is in North African linguistics. So there's a lot of like trying to convince people that yes, like I am a lead machine learning developer. Like it says that on my resume. I've done the work, but I need more of those like certifications kind of things to convince people that I really do know what I'm talking about, I swear. Whew, okay. Alrighty, so we're just gonna copy some more stuff here. This should all look familiar to those of you who were here for previous streams. Thank you. I don't know if I said thank you for following Carl Mint, but if I did not, thank you. And Ovon 10, thank you for following. All right. So, this is me being lazy. Don't look at this. This is me being lazy. That's a half-assed way to shuffle your data. if you have a pandas data frame and you're feeling really lazy and you don't want to use a more elegant way of shuffling it, you could do that, but don't tell anybody I told you that. You didn't see that here. No, Playcraft, you butt. Whatever. All of this is stuff from last time. It should look familiar, but if anyone who is new has questions, stop me. I don't mind explaining any of this. Oh God, and I always do this backwards, so I'm gonna copy this. Sorry, I always do test train split instead of train test split. Every goddamn time, even when I'm thinking about it. It's so annoying. I think I already did a seed, but just in case. Let's be careful. Nikhil 1737, thank you for following. Is machine learning the same as deep learning? It is not. So deep learning is it refers to one, I would say, kind of quality of neural net architecture. So I guess in that sense, you could think of it as a type of machine learning. I don't like to explain it that way because I like to tell people there are three main types of machine learning. There's supervised, unsupervised, and reinforcement learning. There's also kind of semi-supervised learning, which is like the in-between. Deep learning, I hate that they took a similar name there, is referring to a feature of, not feature, because we use features in different ways, a trait, a characteristic of neural nets, of certain neural nets. So it's not even really an approach per se, I guess. It'd be like saying regularization that we learned for linear regression. It'd be saying like regularization learning, and you're like, no, this is how we like change a specific kind of model or improve it. It's not necessarily a type of learning on its own, in my humble but probably wrong opinion. Anyway, okay, so we're gonna do this unsupervised learning. Your child. We're going to use the same thing we did last time. Okay. And we are going to create our bootstrap sampling here. Okay. Did I not? Did I put a... Oh no, I put an extra. Of course I did. Hold on, sorry, I got a message. What on earth? I don't think that's important. I'm not going to worry about that right now. Man, I'm getting weird messages. Okay, all right, who cares? Anyway, what we're doing for this in let's do 10 trees in our forest. And Vigov, as you say, why scaling for an ensemble model? Because I found that so this is scaling not for the ensemble, but for the individual trees. Thank you for following Dev Noah. And as much as people love to say that somehow like decision trees will work without scaling your data, I think it's bullshit, honestly. I have had trees, literally I've run the tests where the trees will not converge. Like you won't get good predictive outcomes fitting decision trees to unscaled data. I scale it and I get great outcomes. So always scale your data, even if you don't think you need to. Napalm Granite. Thank you for following. All right, so we're gonna take 10 trees. We're gonna make a little faux forest here, and it's gonna be of 10 decision trees. Okay. So for those of you who haven't seen the data, by the way, should have done this. This is what our data looks like. All right, so we have these measurements of various features of these flowers, and then their species. And the goal is, can we predict the species of the iris based on these physical characteristics? Arrhythmia, yes, good. I'm glad I'm like gonna engrave that on my tombstone someday. Oh, I love tea. Okay. All right. Getting my voice back. We got this, friends. We got this. I'm gonna do it. I promise. All right. So let's start out with our basic decision tree classifier. Okay. And then we're gonna say for each of the samples, each bootstrap sample in samples, right, is our list of bootstrap samples. Okay. Our training data. And we're like, wait. We need to bootstrap sample from our actual training data. So that's why we're making this like kind of fake X train here. We want everything but the last column, because the last column, this is our label. Okay. And then, and this isn't even like, this is us sort of manually doing it. And I'll show you how to do a random forest from scikit-learn. This is us manually doing it so that I can kind of show you the process. So I would not recommend, if you're building a random forest, don't do it this way. This is me showing you kind of what it looks like. All right. Okay. So what does it look like? It looks like this. So this tree made these predictions. This tree made these predictions. But ideally what we would do is we would average the performance. We would average out those errors. So you can see these trees are performing really similarly. They're making very similar predictions. Reinforcement learning from scratch. We're going to be doing something kind of similar to that, actually. Theoretically. I made all these grandiose plans, and then I actually have to write the code for it. Ariba Juarez, thank you for following. Okay, but here's the thing, friends. Here's the thing. Who the hell just wants 10 trees? Also, bagging. Bagging is how we do it manually. There's another element, right? Random is in the name. And the beauty of real random forests is that we're not just going to randomize our sampling. We're not just going to use bootstrap sampling. We also are going to use random subsets of features. And this is where the beauty, this is where the power of random forest comes through, is that we are using randomness upon randomness, but also this is a really, really cool way to look at feature importance. Boom87 and DXWoo55, thank you for following. All right, so This will also help in cases where you have very sparse data. Remember, if you think back to linear regression and us talking about lasso and ridge regularization methods, we were trying to figure out, how do I get rid of the data that is BS? How do I get rid of the data that is clouding my model, right? Random forests do it by introducing this element of random feature selection as well, which is really cool. Okay, I am writing with Python, yes. Dr. Mumba, thank you for following. All right, so ensemble. This is an ensemble model, right? Here's our first random, what do they call it? Yeah. This is our first ensemble model. And I can't wait for being able to talk about more ensemble models. Oh my gosh. Skipping steps here. Random state, not random seed. And how many trees do we want? How many trees do we want? Let's be bold, friends. Yeah, let's use 500 trees. We just used 10. Let's use 500. So before I do this, remember, when we used a single decision tree on this exact same data set, the most that we could massage out of it was like upper 70s, low 80s. Ensemble models are awesome. What was the score? What did I did it before stream? Yeah, let's see. So that's what I was afraid of. So the problem with the way that we did it here is that I was taking all of the data for sampling because I wanted to show you what it looked like to have all of the different trees making different predictions. So I was doing something a little sneaky behind the curtain, because ideally we would want to sample solely from the training data, where this is kind of like randomly selecting our training data. And an individual tree might perform really, really poorly, and we only picked 10 of them. So that was for the ease also of showing you all of the scores, so you could see all of them. If I picked 100, you would have like 100 lines of scores. So I wouldn't worry too much about the performance of the 10 like fake trees. Also to understand though, we can't compare this because this isn't a real random forest. We're not randomly selecting our features here. We are just kind of like sort of making it bootstrap for ourselves. Luis Paulo and Mesterman, thank you for following. Yeah, let's do that. So I also like going back here and redoing this a little bit. So it reshuffles the data. So 93. Yes. Reshuffle. Where's my shuffle? There we go. All right. Anyway. And now it's going down. Whatever. All right. It's being weird. Yeah. So we went from 93 to 97. Now it's saying, why is it saying 91? Is it doing the same thing it did before stream where I like goofed the names? Hold on one second. I did this because I changed some of the variable names because I was being really lazy before stream in my notes. And it was, I renamed xtrain and xtest, and I had those be the name in the loop. And the problem was it was overwriting my testing and my training data. This is why you don't be lazy, friends. Don't be lazy. Yeah, it's also part of the randomness. Actually, I'm kind of curious. Now that we're messing with this, let's mess around a little bit more. I haven't done this actually. You can get too many trees, but so maybe like I would be interested in plotting just like we did for K nearest neighbors, plotting the number of estimators and seeing. We can also try to prune our trees too. So here I'm letting the trees go as deeply as they want, which means we do run the risk of overfitting. But with 1,000 estimators, you are running way less of a risk. Thank you for following Amadei and Annabelle. So regardless, even if we were to like kind of reperform this over and over again and average the performance, we're still hitting above 90% accuracy when with our singular, our lone, poor, sad decision tree, we were only getting kind of upper 70s, low 80s. So one of the other things that we could do, I could show you, how do I want to do this? Predict, but we're going to need to reshape this, don't we? Yeah, because this needs to take. And then so this is going through, and this is each tree predicting a different element of our test data. Espritart, thank you for following. Okay. So, the other thing, we're kind of going back a little bit here. Yes, all right. Remember how I told you one of the cool things is we can extract feature importance here, because as we have all these different trees splitting on a variety of different random samplings of our features, we're able to see what features are the most important, what features should be kind of the root of our tree, right? And so that's one of the beautiful, beautiful, beautiful things about random forest that brings us a little bit back in our mind to the explainability of linear regression. We can extract the feature importance very easily. So if you remember right, not right. If you remember, I didn't remember. So here are various features. Oh my goodness. Tayo Inue, thank you so much. Math Raid, you are in the right place, my friends. We have been doing some math tonight, actually. Let me find out where did, oh no. Zoom out, please, thank you. Where did our math go? Where was our math? Oh, we got math here. We got some math. We were talking about entropy and talking about entropy and decision trees and entropy in random forests. Thank you, Eric Metterer and iFly Texas for following. So you are in the right place if you like math streams. But we are quickly wrapping up this one quick point here, which is that random forests, we can very, very easily see our feature importances. And look at this, right? log, number theorist, right? log of this. Don't you miss the days when the logs were all base 10 or base E? I wish, right? Learning balance. Hi. And thank you, Enginuber. That's such a great name. Thank you for following. Okay. Alrighty, so what does this tell us? This tells us that, like, okay, sepal length, like, okay, sepal in general, you're cool and all, but when it comes to telling the species of an iris, the petal structure matters far, far, far more. This is really important. And why is that important? I don't know anything about irises, so maybe some botanists can tell you why it's, like, botanically important. Why this is important for machine learning is that models where we can extract takeaways like this are really, really important for explainability and transparency. Thank you, Ramsgold, for following. It's a lot harder to build this massive, deep, complicated neural net and hand it over to a client or hand it over to, like a non-technical CEO, CTO kind of person. Be like, make decisions, see the numbers tell you to. It's a lot easier if you're able to extrapolate important takeaways like this and be able to translate that back into terms of the data and be able to say, hey, when it comes to your wonderful business you've built on predicting iris species, maybe we're building an app. What really matters are the petals. If you're able to take that, what the math is telling you, what the numbers are telling you, and translate it back into English for people or whatever language it is that you're working in, that is really important. And that's when you hear people talking about the explainability of models, that's a lot of times what they're talking about. Is it intuitive? Do we understand what the model's doing? And I'm not talking about our sums and our integrals and all of that. I'm talking about, if I were to sit down in a room with somebody that was afraid of math, could I explain it to them? And with decision trees, you can. Everybody has seen those flow chart memes, right? We talked about that earlier in stream. So this is a really intuitive, explainable, transparent model that's very easy to extract feature importance, which is a critical part of decision making. And so for that, it's pretty great. Gray Cabinet and Fulner, thank you for following. And you say, explaining the models, why would I want to give away my secrets? Well, so much decision making. If decisions are made based on your model, I say that you should be explaining them. But I do appreciate your sass. Sohib said, thank you for following. Okay. And this leads to a cool idea. So we've followed this idea of ensembling, right? We're going to take our decision trees and we're going to cram them all together and we're going to randomize a bunch of stuff and hope that they all average out, right? There's one other kind of ensembling that I want to talk to you about. And we're not going to build it today. But I do want you to be aware of it at least. So let me get my tablet back. Come back, tablet. Hi, ICU. Yes, thank you. I feel much better. I'm still kind of chugging the tea, and I'm losing my voice a little bit, but I'm feeling much, much better. Exactly, V. Galvez. I would say that there are certain fields where that is a lot more prevalent. Emergency management, first responders, doctors. There's kind of like, I almost feel like people who work in a crisis situation a lot of times really need to understand a lot more. I've definitely worked for people where it is more hand wavy and they're like, you figure it out and like make it work and hand it to me. But there are a lot of people in a lot of different industries where explainability is very high for them. Very, very high importance. And honestly, for me as a developer, it's very much an area of importance for me too. Because even if the client's like, I don't care, just build it and make it work. I'm like, well, I control the slides, and guess what? I'm going to sit here and spend a couple of slides at least explaining it to you so you understand what you're getting. Like, I don't think people should use tools they don't really understand as much as we're able to. Cotter, thank you for following. Especially if those decisions are very impactful. Please enter valid username. So what is this learning on holidays? I know, right? This is I swear. I think my parents and some of my friends were just like, are you serious? Because I was like, I'm finally taking 2 weeks off from work. And then I was like, I'm going to do 12 streams on machine learning. And they were like, take a break, play video games. I was like, no, I should do all these streams. V. Galvez, thank you for stopping by. Yeah, ask all the Ensemble questions on Discord that you want. Go for it. Okay. So the thing that I wanted to introduce you to is something called boosting. Assuming we're actually learning it. Hey, I'm trying to teach you. Don't be hating. Okay, and so what is boosting and how does it differ from random forest? So the idea is that we're gonna take an okay model, right? We're gonna call this our weak learner, okay? And then we're going to, instead of random forests, right? Where in random forests, if you remember, which you should because I just explained it to you, In random forests, we train all of those trees separately. They're independent. So it's not really, I guess, like a forest, because forests are all like collective organisms, right? But in this way, you've got a whole bunch of trees all kind of like, maybe they're all trees in pots sort of growing together, right? They're separate. And thank you, Uppermost. I'm glad. So in the case that we're going to talk about, we're going to talk about shallow, or maybe if we're sticking with our language here, our heavily pruned decision tree. Unlike random forests, which have those independent trees learning by themselves, in this case, we're going to add one tree at a time. And each of these trees is actually going to be working on the outcomes and everything from the previous tree. So it's going to help correct errors made by the previous tree. So it's different than our random forest. So random forest, all these trees are independent and we're averaging the results. In this case, each tree is kind of working off of the previous tree. And so this is interesting, right? Because random forests tackle the problem by bootstrapping and having all these trees independently and randomizing a bunch of stuff and averaging it out. If your data is really, really unbalanced, though, let's see, then boosted trees are going to work a lot better. So this is gonna perform better with unbalanced data. So actually, this is a model that works really well for anomaly detection, which we'll be talking about on another day. However, the downsides, there's always downsides, right? Is that it can take longer to train. It's harder to tune. And unlike random forests, it's more prone to overfitting because we're removing some of that randomness. So you might be like, okay, well, what the heck? Like, both of these models have pros. They both have downsides, right? Well, the point here is that every single model has a situation where it's going to succeed and situations where it's not going to succeed. So a lot of times when you're first starting out in machine learning, you can kind of think, oh, this model's great, it's so great. And then you see its limitations, like, man, this model's trash. And then you learn on, you move on and you find another model. Like, oh, now this model's the new greatest model. And you can kind of spot like the early career machine learning people for that reason. They get obsessed with like one kind of model. And really, each of these is a tool. It's like being obsessed with a Phillips head screwdriver. It's like, it's great for certain situations, but like there's going to be a lot of situations where it's not going to work. Models are like that. They're a tool in your toolbox. And gradient boosting is not related to this. Gradient boosting is kind of related to this. So we're not going to be talking about gradient boosting, but chat me in Discord, Strawberry. I think you're in the Discord. And we can talk more about gradient boosting. Adam Savage would disagree. Every tool is a hammer. Well, Adam Savage can disagree all he wants to. I'm right. Shots fired. No. But seriously, each model has types of data or types of situations that it succeeds on, and it's going to have downsides. And the important thing is to understand the weaknesses, right? Because this is a tool. And when you deploy it in a situation and you're like, okay, here's data nobody's ever worked with before, and I've got to build a model to do something with this. How the heck do I tackle this problem? If you understand the various kind of classes of models, the various groups, and you're like, okay, well, my data has these attributes, and these are like the priorities. Like, you know, maybe I'm in a situation where I don't care if it takes a long time to train, and I've got infinite compute resources. Wouldn't that be nice? But, you know, maybe the data's really messy, and there's a lot of outliers, and, you know, a lot of those multicollinearity problems and things like that. Well, then you're going to pick one kind of model. But if you're like, no, I need this thing to move fast, and it can't spend a lot of time training, it can't use a lot of compute, but, you know, the data is going to be really, really clean. Well, then you're going to use a different kind of model. understanding the pros and cons of each model allows you to understand like what tool to pull from your toolbox when you're facing different situations. Anna, you say, do you recommend going into ML as a career? You're a CS student. Do I recommend it? Well, depends. Like, if you really like it and you find it interesting, I would say go for it. There are downsides to every career field. I would say that if it's something that you're very, very interested in, obviously I'm going to be very encouraging. It's kind of hard to say, do I recommend a specific field over another field? Like, I've worked a lot of different careers at this point, and they've all had their pros and cons. Zalbag, thank you for following. Perceptron for the win. Oh, God. Like, it's cute, don't get me wrong. But, like, it can be kind of frustrating to be brought into a situation where, like, you have a more naive kind of client, and they've gotten kind of more of a junior machine learning person, which is totally fine. And that machine learning person is like really excited about one model they read a paper about. And so even if it doesn't fit, even if it's not the best tool for the job, they're like, this is what we're going to do. And it doesn't work so great. And so like eventually I get pulled on to like help or consult or something. And I'm just like, what did you do? Like, what tests did you do on your data? Like, what cleaning did you do? What, statistical analyses did you do of the distribution of your data? And they're like, no, but I built this really cool neural net. And I'm sitting there like banging my head against the wall. Like, all models are actually interesting. Okay. They really are. They're cool in their own special ways, and they all have their own pros and cons. But it's kind of like cooking. You don't bake every single like ingredient that you come into contact with. You don't boil every single ingredient you come into contact with. You learn a variety of different techniques that you can apply, sometimes in different combinations like ensembling. But you use them in different scenarios. And the strength is knowing how and when to use different models and how to interpret the results. Like, just because you pull out your, random forest and you train it on your data, and you're like, why is it getting me a 20% accuracy? Oh, this model's crap. You have to understand what it's doing. What kind of like hyperparameter tuning have you done? What kind of data are you using to be able to interpret the model's results as well? Oh, Rude Guy, thank you. I know, I like this. I wore this too because my mom was on stream earlier, and she bought me this, so I got to show off for my mom, all right? Uppermost, thank you for subscribing. Thank you so much. I'm so glad. Thank you for the support. This is day 4 of 12 days. So for those of you who are new to the stream, you are coming at such a good point. 'Cause look at this. You're not even halfway through. You have 8 more days of wonderful machine learning goodness headed to your Twitch app. Yeah, that failed. Torlac, thank you for following. Torlac say you just got here and you feel like your life is being exposed. Different industries, same pain. Fussy Kid, thank you for subscribing as well. Oh my goodness. Aw. It's like a Christmas present. Thank you. Like, as silly as it sounds, if you let me be just a little bit cliche for a second, thank you for following Learning Balance. The support really does mean a lot because, like I said, I've got 2 weeks off from work, and I'm spending a couple hours at least each day finding data, designing the streams, writing out the notes, the code, testing it, making sure it works. And like, this is time I could be spending in my PJs doing nothing but playing video games. So it means a lot to me that you find the content, useful, and that you're enjoying yourselves and you're learning something. And I appreciate the support. And you say you're pumped for unsupervised learning and network analysis. Well, just as good, Joe. Network analysis is very, very cool. Not to burst any bubbles, unsupervised learning is hard. Yay! Non-dairy neutrino, thank you! Thank you so much for the sub. And non-carbon and stir-fried crazy, thank you for following. Thank you so much. But yeah, just as good, Joe. Loafbone. Oh my god, he's doing that because there's a hype trade. Thank you, Loafbone. My goodness, thank you for the subs. You and your gift subs. You love Hype Train so much. Thank you. Now all of those people, Root Guy, Jords and Z, Albel, the real Pygon and Generic Crew, you are all stuck with me now. Ian Alex Hart, thank you. And Reboot to you. Now you have a sub. Thank you so much. And I'm so glad you were one of Holy Moly Mo's gift subs. That was quite a stream. That got me quite flustered. So the real Pygon, do you want to use your cheer? Do you want to use your cheer to give my dogs treats? So if you cheer 100 bits or whatever they're called in stream, it allows you to give my dogs a treat if you would like to. I can pull up the camera. Just give me 1 sec. All right, we'll go real quick to the just chatting while I set that up. My dogs are like, yes, please. So let's see. Nope, it's for me. You don't want to give. You. Thank you, Alta4. Oh my goodness. Thank you. You're just trying to know. This is payback. This is payback because I dropped those gift subs in your stream and you got so flustered you left the room. So you're just you're paying it forward, but in that way of like trying to make me all flustered. Thank you so much though. And Acromonic, Kuzma Troublemaker, Gian Drop, Jhend3D, and Nomad Derek. You're stuck with me now. Oh my goodness, Ian Alex Hart, thank you. Thank you so much for paying forward your gift subs. And whether or not people actually want to treat my dogs, I mean, we should probably give my dogs treats. Let's be real. Thank you, Love Phone. Subscribe for 23 months. So not since the start, though. Because, wait. Isn't my stream? Hold on. Dang, that meant you watched my stream for a year and you didn't sub. Oh, I'm judging you a little bit. Because the stream's 3-year anniversary is New Year's Eve. So Love Phone's getting called out a little bit here. No, Love Phone's our mod. We love Love Phone. Oh my goodness, Real Pygon, thank you. Thank you so much, you all. Look at this hype train. Hype trains are so exciting. I don't know why there's a countdown. It stresses me out a little bit, and I don't know what the percentage is, but I know that this is something good, and people get cool emotes and stuff from it. So thank you. But the countdown, it's like, what's going to happen? Like, why is there a countdown? Hubblecam, I'm making it happen. Hold on, I'm loading it. It takes a second. It's like slow as balls because it's like a little simulator. But beta, let's see, Casado Conejos. Oh yeah, that's something with Married with Kids, I remember. Beta Go, Blowfish Fugu, Alson FX, Snakebite 39. Now you all have subs. Oh no, the Furbo says it's a connection. No, okay, it's connecting. Hold on. Hubble. Let's get Hubble here. let's get the dogs up. We got to get the dogs up for this. I fly. Oh my goodness. 6 months of a sub. Thank you. I didn't even know you could do that. You can sub in advance. Oh no, the Furbo's lost network connection. Love Phone, can you restart it? It's going to try again, but we might need to restart the Furbo. Level 5, is that what it means? Okay, it's at 125%. Yay, thank you. Is that the like sparkly heart? Is that why? How do I see what emotes I have? Does it give me emotes or does it just give everybody? I hope it gives everyone else emotes. I don't even really know the emotes very well. Left one, can you unplug the Furbo and replug it in, please? Thank you. Merci. Thank you so much, all of you. This is very, very, very sweet. And let's see, we did have some follows in there. I want to make sure people don't feel left out. A War Bear. I Bite Hard. New one, 177. And Claren Haw. And let's see, did I miss any others? I don't think I had Stir Fried Crazy. I think I got you. Yes. So thank you all for following as well. The follows, the subs, all of it means so much. Thank you. And yes, oh my goodness, 500 bits. Does that mean I've got to give my dogs five treats? They're gonna like. Hubble's allowed to. He's allowed to get a little chonky during the holidays. It's okay. We all kind of do, you know. So he's allowed. No, the Furbo is still saying lost connection. Okay, I'm working on it. We're debugging this. Hold on, friends. Let me pull it up. Holy crap, non-dairy neutrino. Seriously? That's... Whew, goodness. That's quite a bit. Oh, there we go. It worked. All right, so hold on, friends. We have debugged this. Okay, so let's see. It'll make a noise, and let's see if we can get Hubble to come over. And do you like make sure there's 2 lonely presents? I don't think... Oh, here's Hubble! Here's Hubble! Everyone say hi to Hubble. This is Hubble. He's my dog. He's very good. He's a very good boy. And let's see. I guess we owe him 6 treats. So here's treat number 2. Probably going to hit him. He's like, oh, God, here we go. I love this so much. Isn't this really fun? This was something that, you know... Thanks to all of your subs go to pay for things like my tablet so that I can write better notes and you all aren't like, oh God, the mouse writing. No. Oh, here's Tenn. Here's Tennessee. Here's the other pup. Oh no, he's running away. I don't know why he's running away. Oh, he heard me say his name. So Tennessee, no. Baby, oh my God. He heard me say his name and so he ran towards my office. This is the XP Pen tablet. It was actually quite affordable, but it was made even more affordable thanks to Stream. I know he heard me, little bean. And, you know, things like my green screen. Oh, good boy. Look at him. He's such a good boy. And things like the Furbo and our programmable LEDs that we have on streams where I'm not really doing programming and we're not able to have the green screen. Here he is. Here's Tenn. Let's see. I can talk to him. Hold on. If I pull up the Furbo. Oh good. He got a treat too. I'm like trying to throw it directionally, which is not how the Furbo works. What's the emoji? Oh, the little like, oh, I like it. Look, there's like a little like wizard thing too. This thing. That's really cute. All right, hold on. So I gotta pull it up on my phone because for some reason this little emulator won't let me. Tennessee. Are you ignoring me? Tennessee. Hubble. Are you a good boy? Are you a dog? Look at that. Are you a dog? They like that word. Head tilts. Hubble, Tennessee. Are you good dogs? Are you? I love you. Do you want boys? Do you want treats? You want a treat? Tennessee, Hubble, you want a treat? All right, sorry. Okay, I got a little distracted there. Little head tilts of like, what's she saying? They love the word dog. And I swear it's because it's the first word of dog park. And so, or dog, like, no, it's not like, and daycare starts with dog. And those are D, and those are the things that they love so much. And so, oh my goodness, such good boys. So thank you for those of you who donated bits. My dogs, thank you very, very much because now they are full of wonderful treats and enjoying themselves immensely. Hubble and Tenn are both very good boys. And we frequently end stream with Tennessee singing, by the way. So actually, let's, we can get that started. Start to set up. So I need y'all's help figuring out what Tennessee should sing for you. So he will sing any of the Star Treks except Enterprise. He will sing Stargate SG-1 and he will sing Stargate Atlantis. And so if you would like to make your choice, let's see, I can try to get us I will get us a straw poll if you give me 1 second here. I'm a little bit slow. Tenn has very good taste. He's a very good boy. Straw poll. wish I could just save the same straw poll. TMPOR on Hero, thank you so much for following. 300 bits. Oh my goodness. Thank you, Playcraft. Are you just trying to give my dogs more treats? Oh, Lovebone is miles ahead of me here. Oh, he sings SG1 non-dairy neutrino. He does indeed. So we've had TNG the last few streams. So I would encourage all of you to vote here. Let's see. I will switch it back to our, so you can see our votes here happening in real time. Manbrave TV, Michael Aranda, thank you for following. And while you all are voting, and there's all this wonderful contentious voting, it looks like TNG and SG1 are neck and neck now. I'm leaning towards SG1 just because TNG we've had it the last 2 streams. I'm going to go get Tennessee. The diva has to be prepared, okay? Don't go away. It'll take me a couple minutes. I just have to pull down the green screen. But when I come back, you'll have a wonderful singing dog who will serenade you. So get ready, all right? Don't go anywhere. I will be right back. Hi, everyone. Okay, so Tennessee is here with me. I am setting up for his solo. Give me 1 second here. Webcam. I need to remove the filter that crops it so you all can see how beautiful and wonderful he is. All right. There you go. Focus here. Look at him. He's getting ready. This is Tennessee. He's going to sing for you today. And it looks like he is going to sing Stargate SG1, which is my vote too. So, woohoo, go stream. All right. Are you a good boy? Do you want this turkey? Oh, shit. Good boy. Sit. Okay. You're a very good boy, Ted. Sit. Sit. Close enough. Good boy. Stay. All right, a little bit of a volume warning. I'm going to turn it down, okay? He gets very loud, but get excited. Here we go, Tenn. Oh no, it's connected to my headphones. Hold on, Tennessee. I love you. It's okay, Bat. It's okay. boy, Tennessee. You're a very good diva boy. He nailed it, exactly. Excellent, excellent, excellent boy. All right, my friends. He's a very good pup. Let's rate a small stream, by the way. Thank you, Chill Gunner, for following. So let me see here. We've got a couple different options. Also, be sure to come back tomorrow, as you can see from the. I'll shrink myself here so I'm not blocking the the schedule. Tennessee was more important than the schedule for sure. But let's see here. Actually, I've got somebody for us to raid. We're gonna raid Volcano Doc, who is really, really awesome. A volcanologist. Oh, wait. Okay, hold on. No. Well, yeah, let's do Volcano Noir. Yeah, Lantern Noir is on. He's doing Sea of Thieves, so I try to raid science streams. So please try to stay by, like throw a follow. I love raiding smaller streams, giving them the love. Come back tomorrow. Tomorrow we'll be doing K-means. We're starting our unsupervised learning segment. I know, Tennessee, you're a good boy. So please come back tomorrow, 7 p.m. Eastern Standard Time for all of the streams. And yeah, we'll be entering into the difficult time of machine learning. So if you think it's been hard so far, prepare yourselves, my friends. This is where it gets tough. But please try to throw Volcano Doc a follow. She's really cool. All right, and I will see you all tomorrow. Have a good night.